Welcome back. No discussion of Newton's laws would be complete without his third and final law. So firstly, in this video, we're going to define his law. We're going to look at examples of why it's important to consider. We're going to introduce our trail drawing code that we've played with the little yellow arrows, but now we're going to start to understand how that works. We're going to switch the trail direction around because once you understand Newton's second law, you'll realize it's wrong. Full marks if you've spotted that already. And we're going to have a recap of Newton's laws. So what's the third law? Well, according to Wikipedia, it says, when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. Cool. So what does that mean? That means that the chair that you are sitting on is pushing up on your bottom exactly as hard as gravity is pulling you down towards the earth. It means that the gravitational force between the monitor you're looking at, the screen you're looking at, and your face is the same as the force in the opposite direction. Yes, there's a gravitational force between those two. It's absolutely tiny, as we'll see later, but it's there, right? And there's always a second force. In all circumstances, there is a second force. In fact, this is exactly why planes fly. Yes, there's a more complex explanation to do with air going over the top and bottom of the wings. But the reality is aeroplanes fly and helicopters fly because they hit air molecules downwards. And in hitting air molecules downwards, they get a force upwards. In every single circumstance, there is a second force to be considered. Typically, in game engines, they forget about that second force. We use air drag without considering the effects of the body on the air, the fact we're leaving turbulence in the air. We can use gravitation like we have a gravity of 9.81. Things start accelerating downwards, forgetting that when you drop a tennis ball, the Earth moves up towards it very slightly. Newton's third law is everywhere. You can't get away from it, and it's super important. So what are we going to do to understand Newton's third law better? Well, firstly, our trails. I've got a little challenge for you. Our trails are around the wrong way. If we dive into our engine, and let's just give our ball maybe a force of magnitude 10 in the x direction. Now let's have a look. Let's play. Back to the scene view, double click on the ball. Now look at this, you can see the coordinate axis. Sure, the arrow is drawn in the x direction and that's the way it's going, but of course if the arrow is to be representing a rocket trail coming out the back of the ball, which is what we're going to be talking about with regards to Newton's third law, then the trail needs to be round the other way. So let me briefly introduce you to the draw forces code. Here it is. It has some annotations that say I'm only allowed one draw forces component on a particular object. So what that means is back in the inspector, click on ball. We're only allowed one of these. The next thing it says is it requires a component of type physics engine. So if again we're on the ball, we must have this physics engine script because it refers into its force list. And then a bunch of other stuff happens that we're not too worried about for now. But down here is where we draw each of the lines. Now the lines are set 2 points at a time, so for each force vector in the force vector list, we draw a line at index I, which starts off at 0, from vector 3.0 relative to the object, because up here we said don't use world space, use local space. So from the center of the object in question, i.e. the center of the ball, to the next point on the line, the next one up, is the force vector. So we're going out in the direction of the force vector, which is why over in Unity what we see is this line being projected out in the direction of the force. We just want to reverse that. So it's a very simple challenge. I want you to reverse the little yellow trails so that they face the other way. If you really want and you want to spend some time, you could use particle systems instead of these trails. And we'll be doing that later in the course. But for now, I just want you to make those yellow arrows face in the opposite direction. Okay, so this is how you do it. It couldn't be a huge amount simpler. It's just this force vector. You need a minus in front of it. That is the change you need to be making. The purpose of this is just so you get some understanding of this draw forces code, rather than it being a mystery black box. Now, if we pause first and play, you see the arrows drawn in the other direction. All this addition will still work properly, so if we add in a second force, not 21 forces, that's too exciting. Let's add in a second force. And just put something like 5 in the y direction. And then we need to advance a frame for it to be drawn. There you go. So we have a force that is in positive y, and so the thrust needs to be coming out the bottom. Now this is the essence of Newton's third law, is that if you want a rocket to go, let me just have a single force, to the left of the screen, or to the positive x direction, obviously the thrust, the rocket fuel needs to be ejected out in the opposite direction. And of course that's how a rocket works, right? It throws mass out in one direction and gets moved in the other. In fact, in deep space, it's pretty much the only way you can possibly move yourself is to eject mass. If there's no sun, no solar wind to catch, and again that's about catching mass from the moving photons, then how else can you move yourself in deep space? So the first thing we're going to need to be doing is creating ourselves a rocket engine so that we can move our space football around, because right now he's sitting abandoned in outer space and moving through artificial forces we're adding, but we need to be actually modeling these forces. So let's recap Newton's 3 laws. In pseudocode, the first law says that if the sum of the forces is 0, then the delta v, the change in velocity, is 0. Now, there are things that are vectors are in bold. The sum of the forces is 0, and the zeros are 0 vectors, as with the delta v. Okay, second law. The acceleration vector is the net force vector divided by the mass of the object. So acceleration is force over mass, or if you rearrange, then force equals mass times acceleration. That's a rewrite of F equals ma. Of course, the mass can change over time, as it will with a rocket engine, right? As we burn off fuel and we eject mass, our mass drops. What happens to the acceleration? If my rocket is out in outer space and it's firing at a continual force, single net force, and the mass of the rocket is dropping over time, what's happening to its acceleration? Well, if you said it's increasing, you're right. It's exactly what's happening. As the rocket burns off fuel, its acceleration will increase, even out in free space. Cool. And then the third law says that if A exerts a force on B, then B exerts an equal and opposite force on A. Notice the minus sign. Force A on B equals minus force B on A. Everything that's a vector is in bold. Mass isn't. It's a scalar. And that's it. Now, this covers a huge range of physical phenomena, practically everything you're going to experience, which is why we start here. Now, I'm not limiting the course to that. If you want information about quantum mechanics and other parts of physics that go outside, absolutely, I'll include it. Just let me know. For now, all you need to know is what the boundary conditions are. You need to be careful when you're below 10 to the minus 8 meters, roughly, very, very small scale, like microelectronics, superconductors, or when you are at speeds anywhere near or approaching 10 to the 8 meters per second, i.e. getting somewhere towards light, like GPS satellites zipping around. They need to make relativistic corrections. But for now, let's get Newton's laws down. If you want to be reading more about this stuff, you can go to the Wikipedia article on Newton's laws here. You can click to see that it is a branch of classical mechanics. And then if you scroll down the classical mechanics article, you will see a diagram here which gives you some idea of the domain of validity. I've used very slightly different, more conservative numbers for you. So that's it. I'll leave you with a summary of Newton's laws. Congratulations on getting this far, and soon we will be building rocket engines with variable mass and acceleration and all sorts of fun stuff. See you soon.